Hey guys, welcome back to another video. In this one, we're going to talk about something called a linear function. And before we get into specifically linear functions, let's talk about what a function in general is. Now, a function later on is going to have a more complex definition and be more visually based. But right now, I'm going to introduce the concept like this. Imagine you had a machine. It looks like a box. And you put numbers into this machine, and it does something and it pops numbers out. So let's say I plug in the number 2. I stick 2 into this machine, it does something to it, and then it pops out another number. Let's say 5. Now it's important to know that whatever I plug into this, the machine stays the same. So it's always going to do the same thing to this number. I don't know what it is yet. So maybe I try a different number. I say 7, and I plug that in there, and it does something to it, and it pops out the number 15. Or let's say I plug in a different number. I don't know. It could be literally any number. 10. And it does the same thing to that number, and it pops out 21. Okay, so the point is, I have this machine. I can plug anything into it I want. It manipulates it somehow. It changes it and turns it into a different number. Okay. Now, it's going to do the same thing to every number. That's important to know. These are not random. So let's figure out what this thing's doing to him. Now, you may have actually already figured it out, but if you haven't, let's kind of make a list so we can keep track of this in our minds. I'm going to make a little table here. If I plug in 10, I get 21, as I just did that one. What else did I say? I plugged a 2 in, and out popped a 5, right? So we've got that one. Let's see. What else did I plug in? I think I plugged in a 7. And that's going to give me a 15. So if I plug in 7, I get 15. By the way, this is my input and this is my output. Okay, that's the table. We could plug in, doesn't matter, I could plug in a 4. Well, if I plug in a 4 to this machine, it's going to do something to it, the same thing, and it's going to pop out a 9. All right, and I could do this on and on forever, and that's something I want to make a point of. These numbers I'm picking are any numbers. They could be random. I could pick them in order. I could pick 10 million. I could pick negative 37. It doesn't matter what I pick. I can plug anything into this. And this, when I teach this in class, it kind of confuses people because they're like, I don't understand what's the problem here. Like, what are you trying to get me to solve? I'm not trying to get you to solve anything right now. All I want you to see is there's this thing called a function, which is this box or this machine, and it turns numbers into another number. That's all I want you to see right now. Now let's see if we can figure out what's happening to these numbers, because it's the same thing for each of these pairs of numbers. Something is happening, but I don't know what. Now, if you haven't figured it out yet, I highly encourage you to pause the video here, see if you can figure out what I'm doing to 4 to turn it into 9, or what am I doing to 10 to turn it into 21, or 2 to 5. It's the same thing that's happening every single time. So pause it real quick, give it a shot, and then come back and we'll talk about what that solution is. Okay, hopefully you figured this out already, but if not, that's okay. So what I'm doing is, when I plug this number in, I'm doing something to it every single time. And if you haven't figured it out yet, I'm multiplying by 2. Let me just write this out in English. Multiplying by 2. And then I'm adding 1. That's what I'm doing. That's what this machine is doing. It's just taking whatever number I give it, multiplying by 2, and adding 1. And then it pops out another machine, or another number. Okay. Let's see if we can write this down more mathematically. I need a way to plug something into something else. Usually when we do that, if you guys remember when we talked about expressions, an expression is something that you plug something into, or you can plug something into. And remember, when we had an expression, we had numbers, we had x in it, had y, sometimes other variables. What we need here is a variable to plug this into. So what I'm going to do is have a variable. Let me get rid of this real quick. X, and that's where I'm going to put my number. And This machine was multiplying by 2. Well, how do I write that? Well, it's 2 times that number. And then I took that number and I added 1 to it. So this is the mathematical way to write the rule that is this function. Okay, so you can think of this as a rule for turning these numbers on the left into these numbers on the right. Multiply by 2 and add 1. All right, now let's make this a little bit more formal. So I'm going to introduce something called function notation. So function notation is just a better way to write what I just did. Instead of writing a box and thinking about it as a machine, this is the way we do it in mathematics. Let's use a different function this time. Let's do that one. Okay, so first of all, this part should look pretty familiar. This says to multiply whatever number I put in by 3 and then subtract 1 from that. That's what that means. But on the left, this might be a little bit confusing. So this here is just the name of the function. I need a name so that I can talk about this function because there might be more than one function. There might be more than one machine that we're playing with. We could have 2 or 3 or a dozen. So it's useful to have a name to call this thing. And so that's what that is, f. I could have chosen any letter, doesn't matter. And then this thing right here, that's the input. This says things that look like this are what get plugged in. Okay? And that may not make much sense right now, but when I do an example, you'll understand. So here's what we do. Let's say we wanted to plug in the number 2 into this function. In other words, from our thought experiment a few minutes ago, I'm putting 2 into this machine and I want to see what comes out. Well, here's how you do that. You would say the function f, and I want to plug in the number 2 into it. And I want to find out what it gives me. Well, the machine takes that 2, puts it everywhere x is, and then crunches the numbers. So 3 times 2 is 6, minus 1 is 5. Now, you don't have to write out all this stuff. You could have just, if you did it in your head, which is fine, f of 2 is equal to 5. That's the shorthand version of it. And what this says is, if I plug 2 into this machine, out pops 5. It's the same exact thing we started this whole talk with, but it's written mathematically instead of using a picture in a box. All right, let's do another one. So I could literally plug in any number I want. I could say f of, let's do 6. That says take the number 6, plug it into the machine that is f, or the function that is f, and tell me what you get. Well, 3 times 6, I'll write it out again. 3 times 6 minus 1 is, that's 18 minus 1, which is 17. And again, you don't have to write all this stuff out. You could just jump straight to the answer. So let's do another one. F of 10. So 10 times 3, 30, minus 1 is 29. I could do negative numbers. F of negative 2. Negative 2 times 3 is negative 6, minus 1 is negative 7. So all we're doing is we're taking numbers, plugging them into this thing, and seeing what pops out. Okay? So far, so good. Well, so far, we've only been plugging in random things, and that doesn't really... Okay, so where's the problem, right? What are we trying to do with this? What's the goal? Well, we're trying to describe a relationship between these numbers. The relationship is given by this thing. This is a rule that tells me how to turn 6 into 17, or how to turn 10 into 29. But that's still very abstract, because on the surface, they look like just random numbers, right? It's kind of hard. We're visual creatures. We want to see physically what's happening, okay? Because otherwise, these are just numbers. Well, that's where this thing comes in. So let's do the same thing again. We're going to use a different function. Let's call this one, well, we'll call this f again. And let's make this one very simple. 2x plus 3. Now we're going to do the exact same thing as we did before, we're going to be a little bit more careful. So I'm going to make my table. Here's the things that I'm plugging in. I'm going to call those X's because that's what I'm plugging in. And the thing that comes out is f of x. That's the answer when I plug in f. On the left, let's plug in some numbers. Let's say I plug in the number 1. All right, well, 2 times 1. Actually, let me do that scratch work up here. 2 times 1 is 2, plus 3 is 5. So I'm going to write that in my table over here. Now I'm going to take that information and see if I can represent that visually over here. Well, if I think of this line over here as my input and this line over here as my output, then this pair of numbers will fit over here on this picture. So if I go on the input, I go to 1, which is right here. I'm not going to draw it, but you can't see my hands. I'm going to show you right now. And then I go all the way up to where the answer was, which was 1, 2, 3, 4, 5. That's where I'm going to put my dot. Okay, let me now erase all the things I just added to this picture. So this dot right here represents the fact that I plugged a 1 in and I got a 5 out. That's what that says. It says if you plug in 1, you get 5. Let's do a different one. Let's try a different color so we can keep these color-coded. Let's do, I don't know, -3. Random. So -3, I plug in -3, is -3 times 2. Let me do that scratch work real quick. Is -6 plus 3 gives me -3. So when I plug in -3, I get -3. Okay, so my input is -3, so I go left 3, and then output is -3, so that's down 3. And there's another point. I'm actually going to label this one too. This is -3, -3. Let's do another one. You can do this all day long. Let's plug in 0. So I plug in 0. 2 times 0 is 0, plus 3 is 3. Okay, so now 0 means that I'm not going anywhere left and right. So I'm going to stay on this axis, and I'm going to go up 3 and put a dot. What about -1? Let's plug in -1. So if I plug in -1, 2 times -1 is -2, plus 3, which is 1. So that means if I plug in -1, I get, not -1, 1. That goes here. Are you seeing a picture? I hope you're seeing what's happening so far. Okay, there seems to be a gap in this picture though. So where would we put another number to fill this in? Well, if we go to -2, I know these are kind of all out of order, but if you plug in -2 times 2 is -4, plus 3, that's -1. So if I go left 2 and down 1, I get this dot. And now you'll notice that this function, this machine, this relationship that's turning numbers into other numbers is not random at all, because it's doing the same thing every time, no matter what number you plug into it. It creates this relationship, and so you can see it visually with a line. And that's why this thing's called a linear function, is because when you plug numbers into a function that looks like this, you will always get a straight line, thus linear function. So I want you to understand so far that there is this thing called a function. It turns numbers into other numbers. And if you put those numbers on a graph, you get a picture. Okay, let's do another one. Just like that. How about, get this color again. Let's call this one G. Now, the letter I chose does not mean anything. I could pick, again, G, H, I, J, K, T, does not matter. But just to show you that I can, let's pick a new one. Let's make this a little more fun. All right. Now, if you want to give this one a shot, you go ahead and do that. Pause it and see if you can create a table and then graph those points. All right, let's go through this. Let's make ourselves a table. So I've got x on the left. Now, I don't think I actually labeled the right side last time. It's f of x, but also those numbers on the right we're putting on the y-axis. So that's going to be our y column, if you didn't figure that out before. All right, now, remember I said that I can plug any number in here I want. It doesn't matter. I could plug in 1, 2, 3, 4, 5, whatever, 10 billion. But remember what the goal is. The goal is to draw a picture here. So the numbers that I plug in here need to be, well, let's see what I've got. 1, 2, 3, 4, 5, 6, 7. Here's 7 and negative 7. So first of all, I only want to really plug in numbers between negative 7 and 7 if I'm trying to create this picture, right? But I can also make my life a little easier than that. Let's think about what happens if I plug in 1. If I plug in 1 here, let me actually do that. So that's 1/2 times 1 plus 2. 1/2 of 1 is 1/2 plus 2. That is 2.5 or 2.5. So when I plug in certain numbers, I'm going to end up getting decimals. I'm going to have to graph, between these grid marks. That's not a problem. It shouldn't be too scary. But remember, I can plug anything in I want, so I don't have to choose that number. If I know ahead of time that I'm going to have to cut things in half, why don't I go ahead and choose some numbers that make my life easier? What kind of numbers would I plug into something if I wanted to not get a decimal? And what kind of numbers would I use when I cut them in half to not get a decimal? Well, those would be even numbers. So let's pick even numbers between negative 7 and 7, like negative 6. Oh, there's my pen. Negative 6, negative 4, negative 2, 0. Because half of 0 is 0, so that one's easy to do. 2, 4, 6. So I'm intentionally choosing numbers that are easy for me to calculate because I can. All right. Here we go. Let's actually do these. So if I plug in negative 6, half of negative 6 is negative 3, plus 2 is negative 1. So that's going to be negative 6, that's left 6, 1, 2, 3, 4, 5, 6, and up, down 1. That's where that goes. All right. I'm just going to stick with the red now that we did the last one multicolored, but this is going to make my life a little easier. Negative 4. Half of negative 4 is negative 2, plus 2 is 0. So when I plug in negative 4, I get 0. That coordinate is going to be right here. Now, if I plug in negative 2, half of negative 2 is negative 1, plus 2 is 1. There's 1, so it goes here. All right. If I plug in 0, 0 times 1/2 is just 0, or half of 0 is 0, plus 2 is 2. So I don't go anywhere left and right, and I go up 2. All right, I can fill that in. If I plug in 2, half of 2 is 1, plus 2 is 3. And the last one, actually, that's not the last one. 4, half of 4 is 2, plus 2 is 4. That goes there. And the last one, half of 6 is 3, plus 2 is 5. And as expected, when I graphed all of these points, which I chose, I didn't dictate to you which ones we did. Remember, we just chose these based on whatever would make our lives easier. But it doesn't matter what I've plugged in. If I plug them into G, I will get this beautiful straight line. So what I want you to get out of this is that these three things, this thing up here, this function, this table, and then this picture on the right, are actually all three the same thing. They're just a different way of looking at it. So you can think of it as this up here. Let me do this. This up here is the rule. It's the how. It's the how these numbers down here change. So this is these are examples of what happens. Let me actually slow down and write words. So these are examples of what you can plug in to this rule. And this picture represents all the different numbers you could plug in. You can imagine if I plugged in numbers between the numbers that I did, then those are going to give you dots too. And all of those dots are going to fill in this line. It's not just a line, it's actually all the different answers for anything that I could plug in. And if you take any number, plug them in, you get this entire thing filled in. So all of this is just the same relationship, the same piece of information, just three different ways of looking at it. And so we're going to try to hopefully get good at going between them, going from the graph to the table and the table to the graph, and then finding other ways to get between them. So wouldn't it be nice, speaking of, let me clear out some of this stuff I've drawn all over this thing. Wouldn't it be nice if instead of having to draw that table out and plug in all those numbers, if I could go straight from here, straight to the picture? Well, if we can find some patterns, then that's going to be very easy for us to do. First of all, notice if you pick any dot, let's pick this dot here. To get from this dot to the next dot, I went up 1 unit and I went right 2 units. Well, where does that appear in my function? Does it appear? Well, it sure does. This is how much I went up, and this is how much I went over. And it doesn't matter where I started. At any point, any dot, that relationship holds. Up 1 and over 2. Up 1 and over 2. Every single relationship for any dot on this particular graph is up 1 over 2. And that is, in fact, where that number comes from. This is called the slope. And also notice this number here, I'm going to use a different color. This number here appears in my graph. Where does that number appear in my graph? Well, it happens to be where this thing crosses the y-axis. So this number we're going to call the y-intercept, because this is where, it's the location this graph is going to cross that line. And this happens to work for every single linear function that looks like this. So, armed with that pattern, let's do another one. But we're going to skip the table this time. We're not going to look at why this works. We're not going to fill in all the dots. I want you to be able to. You need to understand why this picture exists. But if we know these shortcuts, then we can jump straight to the picture without having to do all of this business. All right? Okay. Let's do this one. Let's call this one H. And let's make this one a little less fun if we had to plug the numbers in. But we're not gonna, so it's not gonna really matter much. All right. So remember, this thing we call the slope. And the slope is gonna tell us how much we're gonna go up and over. We call this, if you remember from Algebra 1, that's rise over, well, I said one thing and wrote the other. That's rise over run. In other words, the top number tells you how much you're going to rise, and the bottom tells you how much you're going to run side to side. Well, we got to know where to start, though. Well, that's where this number comes in. So let's go, and this -1 is our y-intercept. So that tells me to go over here on my graph and start right there at -1. That gives me my starting point. So I'm always going to start with that y-intercept. And now my rise over run is going to tell me how to get the next dot from that initial dot that I just drew. So this particular slope tells me to go up 3 and over 2. So from this dot, I'm going to go 1, 2, 3, and then over 2. Oh, I got rid of my dot. So up 3 would be here, and then over 2 would be here. And then I could do it again from that dot. Any dot to any dot will work. So up 3 and over 2 from that one goes here. Now, if you notice that, or you remember this is supposed to be a line, you could also imagine, well, what about the other side? What if I want to go the other way? Well, going down 3 and left 2 is the same thing, just in the opposite direction. So you can do the opposite 2, down 3 and left 2. And then I could do down 3 and left 2 again. And now I have my familiar line. Now, the beauty of this is I didn't have to make a table. I didn't have to plug anything in. It makes it a whole lot easier. The downside to this is that it doesn't tell you what's happening. Um, and that's why I didn't start with this. I could have said, plug that number in or stick that number there and then go rise over run and draw a line. But that doesn't really tell you why you did it. And I wanted you to understand that this line comes from plugging numbers in and getting numbers out. That's what it does. That's what it is. Um, but we can skip that process because we do have some shortcuts. All right, let's try another one. Let's do J. And let's say J is 3x minus 5. Now with something like this, oh, by the way, before I do this, if you want to try this on your own, which I highly suggest, pause it. As I always say, pause it, try it on your own first, and then come back and watch me do it, and we'll see if you get it right. All right, this one's a little bit different. So this one, the slope is 3. But usually we have a rise over run situation. We need both an up and down number and a left and right number. But here I only have 1. Well, if you remember, you can divide anything by 1. In other words, you can put 1 underneath anything and it doesn't change it. So the slope of 3 is actually a rise of 3 and a run of 1. That's what that means. Now my y-intercept is -5. Oh, do a little better job of tracing that. -5, so I'm going to go down 5. 1, 2, 3, 4, 5. Put me a dot. That is my starting point. And now I'm going to use my slope to get to the next one. Up 3 over 1. Up 3 over 1. Up 3 over 1. Up 3 over 1. Now students always ask me, how do I know how many dots to draw? You don't. It only really takes 2 dots to make a line, right? But to make the picture more accurate, dare I say prettier? Oh, well, speaking of, that was terrible. To make it look better, use a few more dots. But I'm not going to dictate how many dots you have to have. Really, you only need 2. All right, let's do another one. How about something with a negative in it? Oh, let me get a different color than white. Let's do k of x. Again, the letters mean nothing. It's just a letter. All right, k of x is -1/3. X plus 2. All right, if you think you can do this, pause it, try it, then come back and we'll do it. All right, now, let's start with our y-intercept. That's easy to do. It's +2. Let me get a different color here. We're going to start here. Now, this is a thing, looking at the slope, this is a little bit different because it's got a negative in it. And this is something that confuses people sometimes. So I want you to ask yourself, if you've never thought about this, when you put a negative on a fraction, does it go with the top or the bottom or the middle? Is it both? Because usually when you see it written in a textbook, it would be -1/3. That negative sign would be right in the middle, right? So does it mean -1/3 or 1 over -3? -1 over -3? What does that mean? Well, what that means is you need to pick either the top or the bottom when you're graphing this. So you're going to have to choose either -1/3 or 1 over -3. What you cannot do is say, well, the negative was in the middle, because sometimes it might be written that way, and so it's both of them. Okay, well, a negative divided by a negative is a positive, right? That's what this is, and that's not the same thing. So do not do this. What you're going to do when you graph these is to choose the top one or the bottom one. And let's actually do both of them so you can convince yourself that this is, in fact, a valid thing you can do. So if you choose it this way, -1 on the top, that's your up and down number, right? So that says down 1. So I'm going to go down 1. And the bottom number is your left and right number. So positive means right, so right 3. Let's actually draw that. So down 1, right 3 would be here. And if I did it the other way, this one here, the top number is now positive. So that means that's up 1. And the bottom number is my left and right number, and negative on the bottom means left. So that means left 3. So that means I'm going to go up 1 and left 3. Well, look. If I do either one of them, it still generates the same linear relationship. It's still going to make a line. Whether I go up 1 and left 3 or down 1 and right 3, it's the exact same thing. So whenever you have a negative slope, just make sure that you either choose the top number or the bottom number. It's one or the other that's going to change. And then you're going to get this beautiful line. All right. Another way to think about that, let me go to a different page. Here's another way to think about this. And this is a really good rule of thumb. So if the slope is positive, so if the slope is positive, oh, that's not how you spell positive, then your graph is going to go up. If you think about driving a car to the right, if you're going from left to right, because that's kind of how forward progress goes, if you go from left to right, you're going up, positive. And if your slope is negative, then your graph is going to go down. It's literally going to slope downhill. So if you think of it that way, you don't really have to get too worried about messing up these negatives like we did over here. Because when you finish your picture, just take a second, and I highly suggest this. Whenever you graph one of these, just take 2 seconds at the end and say, all right, my slope is positive. Is this thing going uphill or downhill? And if it's going uphill, you got it right. Or better yet, do it at the beginning. So notice, hey, this is positive, therefore it's going to go up. Or this is negative, so it's going to be going down as I progress to the right. Right? So it's good to know, what orientation these things are going to go, what direction they go. All right? Okay. I think that's going to do it for this video. I think this should be enough for you to understand the relationship between this rule, the table, and this picture over here, and then do some basic graphing with this type of function. And then in the next video, we're going to talk about a different way to graph these linear functions, and be able to do a lot more powerful things with that later. All right, thanks for sticking with me to the end, and I hope this was useful, and I'll see you guys in the next one.